Well, hello everybody. So, we have come to almost the end of this particular course. So, I was continuing my rather I will pick up my discussions which I was continuing on the different analytical techniques to be used to predict the hydrodynamics of flow, and I was telling you that mainly in order to solve the mass moment to energy balance equations, we have to make several assumptions. Now, these assumptions which we should be making, that depends or that has been decided after observing the different types of flow patterns which we come across during two phase flow. Just like for single phase flow, we solve the momentum balance equation deciding on whether the flow is laminar or turbulent. For two phase flow patterns also, we try to develop a similar criteria. And we observe that if we go through all the flow patterns more or less that we have discussed, particularly in macro systems, we find that we can classify the entire set into a separated flow pattern, a dispersed flow pattern, and a large range of mixed flow patterns, which can be or rather whose schematics are shown as follows. So, from here it is very evident that as we come down to the micro channels, we will primarily be dealing with the dispersed and more importantly with the mixed or the transitional flow patterns. Accordingly, what we have decided is that in this particular lecture series, we shall be discussing the homogeneous flow model, which assumes the two fluids to be completely mixed, and then after that we will be going to the flow pattern based model. And here one of the simplest flow pattern based model is the drift flux model, which is used more or less frequently in microsystems. So, we will be dealing with it, the drift flux model, and then since slug flow is the most predominant flow pattern, we will be dealing with a simplified slug flow model to end it up. And while I go through the analysis, I will be taking up cases for adiabatic gas liquid flows as well as cases or rather how the equations they change when we are dealing with your flow boiling in microsystems. So, now with the homogeneous flow model. Now, in this particular model, as we know, what do we assume? We assume that the two fluids are uniformly mixed and they are flowing as a pseudo fluid at the uniform mixture. Now, what does this imply? This implies that ULS must rather UL, it is not ULS, it is UL, this is equal to UG, which is equal to UTP, isn't it? And naturally, if the two phases, the in situ velocities, they are flowing at the same velocity, it automatically implies that the slip between the two, which is S, which is equal to UG by UL, that is naturally equal to 1, which again implies that alpha should be equal to beta under this particular conditions, and along with that it also implies that there is thermodynamic equilibrium between the two phases. With this, if we develop the model, what do we find? We find that in this particular case we find, so accordingly, so where does the equation come then? The equation, the next thing which we from here, the model which we get from here is that so the equation which we can develop from here is the homogeneous flow equation, which where we get the pressure gradient minus Tp dz, call them, it is equal to tau W2 phase plus S by A plus G du dz, where it is the two phase density at two phase mass flux and UTP plus rho Tp g sin theta, right. Now, in this particular case, what is rho Tp equal to? Rho Tp is naturally equal to g sin theta into alpha rho 2 plus 1 minus alpha rho 1, where alpha is the in situ void fraction, and in this particular case this is since alpha equals to beta, we get this as beta rho 2 plus 1 minus beta rho 1, right. And we can also write, we are fine. So, therefore, this comprises of the gravitational pressure gradient, and this is nothing but the acceleration pressure gradient, and this is the frictional pressure gradient. Okay. So, therefore, from here what do we get? We get from here. So, therefore, and there is something very important about two phase flow which you should be knowing, which tells you that rho Tp and Vtp, they are not exactly reciprocal of one another, or in other words, what I mean is that for any particular single phase flow, we know that the specific volume is nothing but the inverse of or the reciprocal of density. Okay. But if we consider a two phase mixture, even under homogeneous flow conditions also, what do we find? We find that rho Tp, it refers to the weight of say 1 liter or 1 meter cube of the mixture. So, naturally, this gives you, rather it comprises of, say, in that 1 liter of a mixture, we have alpha liter of phase 2 and we have 1 minus alpha liter of phase 1, right. And therefore, the total weight of alpha liters of phase 2 is what? It is naturally alpha into rho 2, and the total weight of 1 minus alpha liters of phase 1 is 1 minus alpha into rho 1, right. And so, therefore, rho Tp is given by this. On the other hand, if we consider Vtp, what do we get? We find that Vtp, it is the volume of 1 kg of the mixture. So, therefore, while rho Tp, it was the weight of 1 liter mixture or maybe 1 meter cube mixture, this is the volume of 1 kg mixture. So, naturally, what does this imply? This means that in this 1 kg mixture, there is x kg phase 2 and there is 1 minus x kg phase 1, right. So, the weight of this 1 kg phase 2, this is going to be x into V2 and this is going to be 1 minus x into V1, right. So, therefore, we find out that while Vtp is expressed in terms of the quality of the mixture, rho Tp is expressed in terms of the volume fraction. Okay. And therefore, it is quite evident that rho Tp or rather Vtp, it is not the reciprocal of rho Tp, or in other words, the expression of rho Tp is in terms of void fraction, whereas the expression of rather 1 by rho Tp, this is in terms of your quality. So, therefore, this is one particular basic thing which you need to remember in two phase flow. This is something very important. We are quite used to thinking that the specific volume is the reciprocal of density, but that does not matter or that does not happen in this particular case. So, therefore, regarding the gravitational pressure gradient, what do we find? Gravitational pressure gradient, it can be expressed either in terms of the volume fraction, and if there is a large amount of change there, then if the void fraction it changes to a large extent, a better way of expressing it is g sin theta by Vtp, which gives you g sin theta by V1 plus x V12, right. Now, regarding the we go to the frictional pressure gradient. Now, what do we find in the frictional pressure gradient? Naturally, this frictional pressure gradient, this is equal to 2 ftp rho Tp, I can write it down, UTP square by d, where this is equal to 2 ftp GTP square by d into VTP, which can otherwise be written down as V1. The VTP part can be written down in this particular form. Now, remember one thing, when we are dealing with microsystems, gravitational pressure gradient is usually not there. So, it is the frictional pressure gradient which is there and the acceleration pressure gradient which is there. What is the acceleration pressure gradient in this particular case? It is naturally GTP, TP means 2 phase of UTP. Why does UTP vary? Can you tell me? It can vary if the area varies, which is true for single phase flow also. It can also vary if the densities of the 2 phases they vary, or if the quality of the 2 phase mixture it varies. So, accordingly we find that VTP, it can, or rather this particular term, this can be expanded as your GTP into WTP by A 1 by rho Tp plus GTP WTP by rho Tp ddz of 1 by A, which can again be expanded as GTP square into ddz of V1 plus x V12, right, plus minus GTP square by rho Tp dA dz. So, we can write it down in this particular form, where, and we have written it down here, where we find that there is, when we consider adiabatic and there is no flashing. So, in that case what happens? This is the frictional pressure gradient, this is the acceleration pressure gradient. In this case, acceleration, it occurs firstly due to a change in area if it is there. Mostly if there is no area change, this term goes away, and then there is one more term which happens because the specific volume, it changes with pressure. So, due to this also an additional pressure gradient happens, and accordingly we find for adiabatic and no flashing case, we find that the pressure gradient can be written down by this particular expression. Now, in this case, I like to mention that we assume that only the gas phase is compressible, which is usually the case. The other phase, which is the solid or the liquid phase, is usually not compressible, and we generally do not deal with 2 phase flows with both the phases compressible, because if we have a gas-gas mixture, that is never a 2 phase mixture, that is always a miscible mixture, and liquids can behave as compressible flows only under very large pressure gradients. If that part is there, then in that case, along with the denominator, we have another additional term. Apart from this particular term, we have another additional term to take into account the compressibility of the liquid phase. Now, this was for adiabatic and no flashing. Now, suppose the pressure gradient is so large that even if we are not giving any heat also, there is some amount of depressurization, and maybe due to that some amount of liquid, it gets converted into its vapor, right. So, therefore, in that case what happens? As the flow proceeds, the quality of the mixture, it changes, and that quality change occurs just because there is a change in pressure. So, therefore, in this particular case, when I was talking about finding out the acceleration pressure gradient, in this particular case, this rho Tp, which is nothing but V1 plus x V12, and in this particular case we had assumed that V2 is a function of your pressure, and that is why it is changing with z. X also becomes a function of pressure, and that also starts changing with with z. And so, naturally in this case we need to incorporate dx dz, which is nothing but dx dp into dp dz. So, this gives me an additional term in the denominator in this case. And suppose we take the most general case where it is that both the phases are compressible and we have a heat input where flow boiling occurs, and along with that it is in the micro channel. So, good amount of pressure gradient also occurs. So, with all these if we combine, then we find that the general expression, it is expressed again as a component of frictional pressure gradient. There is from the acceleration pressure gradient, there is one particular component due to the change in quality due to heat influx. There is one particular component due to area change, if at all it is there. There is a gravitational component, and in the denominator part it comprises of terms due to the compressibility of the two phases as a result of pressure gradient along the flow, and also the change in quality due to the flashing of the mixture, and as a result of which x changes. So, therefore, we have considered all the cases for adiabatic no flashing, then again adiabatic flashing where Q equal to, or the heat input is 0, but anyhow the change in quality occurs. This can occur in microchannels when it is flowing under a significant pressure gradient, and then we have also considered the general case. Now, if you look at the equations very minutely, what do you find? You find that in all the equations almost you know everything. G Tp square, it is the mass flux. If you know the mass flow rate and the area, you can find it out. The change in quality along with due to heat flux and the change in quality due to depressurization can be obtained. The compressibility of the two phases, once you know the phases, you can find out the physical properties from suitable tables, and therefore, this can be found out. And so, you know all the terms which are available to find out pressure gradient for any particular case which you consider. The only unknown which we find is the two phase friction factor. Now, how to find it out, or rather how to evaluate the two phase friction factor? We know that from our knowledge of single phase flow and as well as two phase flow in macro systems, naturally the way to find out FTP will again take some cue from the general practices in macro systems. In macro systems, one conventional thing to assume is that FTP, it is a function of Reynolds number for the two phase, and it is a function of epsilon by d, where epsilon is the, or rather this is the relative roughness factor. Now, how do we define RETP for the two phase system? RETP for the two phase system is naturally dGTP into mu Tp. We know dGTP, I have already mentioned this is G1 plus G2, diameter of the pipe we know. Only thing which we do not know is the mixture viscosity. Here I would like to mention that if it is rho Tp, then it can very well be expressed in terms of a suitable average of the individual mixture densities expressed as a function of the in situ void fraction, right. But remember one thing, mu Tp, it is not a mixture property. This rho Tp is the same whether the mixture is flowing or it is under a batch condition, it hardly matters, but mu Tp is a flow property. Therefore, it depends upon the shear which occurs during the flow, and therefore, representing mu Tp in the way rho Tp or the density of the two phase mixture is expressed, will not be correct. And unless we have a good knowledge about the type of shear which occurs, it is very difficult to find out an analytical expression to estimate mu T p. So, what is the conventional thing which is done? Conventional thing is we propose some averaging loss, some suitable averaging loss for mu T p in terms of composition, and ensure that mu T p reduces to mu of phase 1 for the quality of phase 1 to be 1, or rather x equals to 0 and alpha equals to 0, and mu T p equals mu 2 for x equals to 1 and alpha equals to 1, whatever be the case. So, therefore, these are the two constraints based on which a proper mu T p is expressed in terms of mu 1, mu T p and composition, which can be either the volume fraction or the mass fraction. Accordingly, in macro systems, what do we find? We find that several mu T p expressions have been proposed, and they have also been tried in micro channels, and people have observed that for some cases the Duckler expression is good, a few cases the Schick-Chitty expression is not bad, but in micro channels additional, or rather a few other averaging laws for mu T p has been provided, and Beatty and Wallis correlation is one such important thing. And also we find that during boiling two phase flow, a few other correlations have also been proposed. This has been proposed based on the fact that R12 is flowing in capillaries, and due to flashing the two phase flow was predominantly bubbly. So, therefore, mu T p has been expressed in terms of your homogeneous mixture density and the specific volume of the liquid, and then for high flux boiling in channel, again a second correlation has been proposed. Now, once more I would like to emphasize that it is not a must that you should remember the correlations. The only two correlations which you should be remembering for this particular class is the Duckler correlation, which is pretty easy, and the Beatty and Wallis correlation, which is basically the Duckler correlation with one particular term of 1 plus 2.5 beta. Now, different people, they have worked with different types of correlations, and then they have suggested different things. For example, in that oil water flow paper, for us under certain conditions, they said that the Beatty and Wallis correlation is better, and for some other conditions people said that the Duckler correlation it is better. Okay. Now, it is not, for example, in this oil water flows, if you notice, people have said that Schick-Chitty correlation, this was better for oil water flow in micro channels, whereas the Duckler correlation, this was good for oil water flow in glass micro channels. Well, this was in quartz micro channels, right. And then again there were other people who said that Beatty and Wallis correlation it is suitable for a large number of cases. For example, if you observe the experimental results which I had shown, you will find that for 530 and for 250 micrometer circular channels, Beatty and Wallis correlation was better, whereas for 50 and 100 micrometer channel, the Duckler correlation was better. Now, I would definitely not expect you to remember all these things, but it is very important to know that why so many correlations have been proposed and why under different circumstances different correlations work better. Just observe the two most common correlations are due to Duckler and Beatty and Wallis. If you observe the two expressions, you can understand that for the same flow rates, Beatty and Wallis correlation will give a higher effective two phase viscosity as compared to the Duckler correlation. So, therefore, for any particular homogeneous mixture, we find that the Beatty and Wallis correlation is going to give you a consistently higher mu effective. And therefore, you find that in the 530 and in the 250 micrometer channel, we find that for these two cases, there is a higher pressure loss due to mixing of the two phases. Okay. In these two cases, the flow is predominantly bubbly and slug, and therefore, there is a higher pressure loss due to mixing of the two phases, and the higher value of mu effective, it gives us, or rather it enables us to account for the increased interfacial shear in these two cases in the bubbly and the slug flow pattern. On the other hand, if you observe these two micro channels, in this particular case the flow was predominantly laminar. Here the flow was predominantly laminar, and therefore, there was no need for an enhanced mu T p to account for interfacial shear. So, therefore, it is very important to remember that under the same condition, this gives a higher effective viscosity, and therefore, when there is a extra interfacial shear due to increased mixing at the interfaces, naturally this correlation gives us a better result, whereas when the flow is more or less laminar and the interfacial shear is not very high, then in that case the ductless correlation is better. Now, other than finding out a suitable FTP, a very conventional technique of finding out the frictional pressure gradient can be obtained by defining a particular variable phi square, which is known as the two-phase multiplier. What does the two-phase multiplier do? The two-phase multiplier, it finds out the two-phase frictional pressure drop when it is multiplied with a single phase frictional pressure drop. So, therefore, what it does? It is basically a ratio of the two-phase frictional pressure drop to the ratio of the single phase pressure drop of either of the phases flowing alone in the microchannel. So, in this particular case, finding out the single phase pressure drop is not a very big deal. So, once this can be found out and we can find out an estimate of two phase multipliers from known input parameters, we can multiply the two and we can find out the frictional pressure drop during two phase homogeneous flow. So, in this particular case, we do not need the two phase friction factor, and on the contrary, we can find out the two phase friction factor, rather two phase frictional pressure drop by using a multiplier. So, therefore, we stop for now and we proceed to find out different relationships to estimate the two phase multipliers and predict the frictional pressure drop accordingly. Thank you very much.